Welcome to day 2 of Prog 2020. I'm delighted to see everybody here. Today's session will include 2 invited talks. Christine Tasson from the University de Paris, who will be speaking of semantics for probabilistic programming, and Daniel Ritchie, and she'll be the first speaker, and I'll be giving introductions to the rest of the speakers over the course of the morning session.
Okay, I'm back. I'm just trying to share my screen.
Great.
Okay, can you see my screen? Okay, Rakesh, can you see my slides?
Yes, we can see your slides.
Okay, thank you. So I can start. Sorry for the technical problem. Okay, let's start. So thank you very much for the invitation. I'm very happy to be here and to speak of semantics for probabilistic programming languages. I will present some joint works with Thomas Erhard and Michele Pagani, and it's part of a project on probabilistic programming semantics. So I will start with an example starting from the problem studied by Laplace about the gender bias in the 80s. He remarked that there were less female birth out of the births in this period in Paris. And well, we know how to compute what is the probability to be born female if we assume that the female births are independent and follow the same law with bias, let's say, theta. Then the probability to get F females out of B births is just like this. But the novelty introduced by Laplace is that the bias theta to be born female follows a probabilistic distribution. So he introduced this inference paradigm that we know all, that to understand what is the law of theta, given the total number of female births and the total number of births, we can do like this. First, we sample theta from a postulated distribution, pi, that we call the prior. Then we simulate the data f from the outcome of theta. And we infer the distribution of theta and get the posterior by, for instance, bias law. So in this bias law, we see that we have this integrate that is hard to compute. And because we are a programmer, we will just use a programming language to answer this question. And we will use a program like this to model the probability distribution followed by female births. So it's a probabilistic program is just describing one sample. So if I want B births following with bias theta, I will just flip my icon B times and collect the female that I've got. Now I have my prior theta, which follow, for instance, a uniform law between 0 and 1. I have the data that I want to describe, and I just use an inference engine to adjust the theta distribution by comparison to data by simulation using whatever inference algorithm you want, like rejection sampling, not very efficient, or MCMC algorithm, or your favorite inference algorithm. But here the question is, well, the developers of probabilistic programming languages need to ensure that the implementation of compilers, optimizers, and inference algorithms do not have bugs. And I'm citing this panorama by Page, Yang, and Wood about probabilistic programming. So how can we prove that the implementation of an algorithm is correct, of a probabilistic algorithm is correct? How can we prove that 2 programs behave the same in any context? Like, for instance, if I have 2 different inference algorithms, how can I say that they will approximate the same probability distribution? Well, this is a hard task, especially when you are mixing probability with higher order. Higher order is when you have a functional programming language where programs can take as inputs programs. So there are several questions. Perhaps the most used one is quasi-Borel spaces, but I will present today another solution to that. And to present you these semantical tools, I will first introduce syntax and how we compute with the syntax, and then I will present you two different semantics, one for the discrete case and one for the continuous case. And if I have time, I will show you how we can use them to prove that programs are correct. Okay, let's first start with the syntax. So I have a syntax for probabilistic programming language, a functional one with nat as ground type and another one with real as ground type. So it's a programming language which is based on lambda calculus with loops, while loops, fixed point operator, and natural numbers for the first one. And for the continuous case, I have reals and any measurable function. Then I have a test to 0, and I have a probabilistic operator, the coin, which is a fair coin. It will give you 0 or 1 with probability 1/2, and a sample in the continuous case, which will follow a uniform law between 0 and 1. And finally, I have this storage operator, this memorization operator, and let x equal m in n will first sample the probabilistic program m, store the output in x, and feed n with this x, this output. Okay, so this is for the syntax. Now, how do we compute with this language? So to describe the computation, we use operational semantics, which is using this proba. Proba is an operator, is a stochastic matrix, which is indexed by two programs, m and n, and the meaning of proba mn is the probability that m reduces to n in one step. So if I perform one step of computation, then starting from m, then I will get n with probability this number. So for instance, proba coin 0 will be 1/2, and the probability to get 1 by computing coin will be 1/2 or so. I also have an infinitary version of this operator, and if m is a program with no parameters and of type nat, then this infinitary proba will say what is the probability that m reduces to an integer n? What is the probability that m produces an integer n in any steps, any number of steps? And I have a similar thing for the continuous case, but now proba is not a stochastic matrix, but it's a kernel. So for instance, my program sample will reduce to a program in U. So U is a measurable set of terms. And I have to define this measurability notion about programs, and it has been done by Dallago and so on. And this here will be the uniform distribution. And I have also an infinitary version of that. Okay, so let's move to denotational semantics. It will describe what is the result of my program. So for instance, for a program of type nat, the result will be, the semantics of it will be a subprobability distribution over a natural number. And for a real, it will be a measure over R. For instance, if I take just a natural number, its interpretation will be a distribution over integers, and it will be just delta p n, which is 1 if p is equal to n and 0 if not. And similarly for the continuous case. So what do we want for denotational semantics? First, we want it to be what we call a Cartesian closed category. That means that we can interpret evaluation and querying. We can interpret higher order correctly. And we want that its objects are measurable sets and morphisms are either stochastic or measurable function. There are operators that will preserve probability distribution. But as I said, higher order is hard to mix with probability because the model that we have in mind, which is measurable spaces and measurable functions, is not a Cartesian closed category because the evaluation is not measurable in genera. Okay, so but we have some solutions, some models that are working, and what kind of properties we want on them is first soundness. It means that you can compute the semantics of a program M by knowing the semantics of its radius. So to compute the semantics of M, I will choose a program N such that M reduces to N with this probability, and I will multiply it by the semantics of N, and I will sum over all the possibility. And in the continuous case, it is similar, but with an integer, because here I have a measure. The next property is adequacy, and it means that the way I compute is matching with the denotational semantics for ground types. So if I have a closed program of type NAT, that I know that its semantics is a probability distribution over integers, and I know that the nth coefficient of this sequence is just the probability that n reduces to n in any number of steps. Sorry. And it's similarly the same for the continuous case. Okay, so now we have the general framework, and I will show you two semantics. The first one is probabilistic current spaces, and it's in the discrete case. It is a kind of generalization of the semantics of a Bayesian network. So here I have a simple Bayesian network, a very silly one, but what is interesting here is that the probabilities that the grass is growing can be computed by composition of the probability that the grass is growing, given that the sprinkle is on and the rain and it's raining, and so on. So the condition that we put on a Bayesian network is to have this compositionality. To get the final probability, I just have to multiply these matrices. Here, the fact that the sprinkle is on, knowing that we are in winter, is a simple program. But we can sort of, these things are complex program with, for instance, natural numbers output. So it will be distribution with web, which is infinite. And if we want to go to this infinite setting, we have to find a way to ensure that the composition of this stochastic matrix with infinite indices, this composition stays converge. It doesn't go to the infinite. And to do that, we can use probabilistic current spaces, which has been introduced by Danos and Erhard. So in this model, we will interpret types as objects that are made by a set of finite states, for instance, integers, and a set of vectors, which are the correct distribution, the distribution that we are allowed to use. So a type will be interpreted as an object in this model, which is defined by induction on A, and we can interpret the unit type, Booleans, and any recursive type in that model. The interesting thing is, how do we interpret programs in this model? So if we go back to the Bayesian setting, we can see that a program will be interpreted as a stochastic matrix, which is with index is the input and the columns are indexed by the output. Here it's about the same thing. We interpret a program as a matrix of real coefficients with index input and the output. And we ask that this morphism preserve our probability distribution. But remember, we want to interpret a setting where we can do inference. And for performing inference, we have to sample many times a program, but we are not interested in the order of the output of our samples. We are just interested in the multiset of samples with no order. So we will replace the input by a finite multiset of the inputs so that we can take into account this multiple sampling of the same program. And we ask for the same thing. Our interpretation of a program will preserve probability distribution. So we can interpret a program by homomorphism. This is computed by induction on n on the program. And if we have an integer, the interpretation will just be a probability distribution with 1 on n. And for coin, it will give us 0 with probability 1/2 and 1 with probability 1/2. And we can interpret higher order. And when we do the composition, the property of probabilistic current spaces are such that the composition won't give you any infinite coefficient. All the coefficients will be finite. Okay, so this is a sound semantics. It is adequate, and it is also fully abstract, which is kind of the golden goal in semantics. It says that to know that two programs behaves exactly the same in any context, we just have to show that their interpretation are the same. Okay, so that was for the discrete case. And I move to the continuous case where we have model for the continuous probability with higher order. So our purpose was to be able to interpret real as the set of bounded measures, and we wanted also to generalize the discrete case. So we use a tool which we call complete codes, which is just real normed vector spaces, except that the scalars are positive and there is an order. But in this category, we had this problem that it is Cartesian, but not closed. So we had to change a little bit our interpretation of programs and to move to stable functions, which are defined, which are functions such that the difference is non-decreasing and the difference of the difference is non-decreasing. They are like super convex function. And we get a Cartesian closed category. But there are stable functions that are not measurable. And we need measurability for our interpretation of programs because of this operator. The let x equal r in P operator will be interpreted by this integral. So I have here, P has to be measurable. So we had to add some measurability notion, and we used a standard trick in semantics. And actually, it's the same trick as in quasi-Borel spaces. And we get a model of higher order with continuous probability included. Yeah. So I have, yes?
It's 3 minutes.
Okay, so I have some few minutes to tell you how we can use this denotational semantics to prove that implementation of some algorithms are correct. So let's have a look at this rejection sampling algorithm. So I have a table which is represented by this function, which sends an index to 0 or 1, which is the inner of the cell. And I want to find an index, one index of a cell that contains 0. Okay, so I just do it by rejection sampling, which is implemented by this algorithm. So I'm not sure you believe me that this algorithm is doing that. So I will prove that the probability that I get a success, that is the index of a cell with a 0, is equal to 1. How I do that? First, I use operational semantics. I can reduce this program to this one. Then I use the invariance of the semantic. The interpretation of this program is equal to the interpretation of this program. Because I have the let, I get the sum by the definition of the interpretation. And I can compute that and solve my equation. Now I can use the adequacy lemma. The operational semantics is corresponding to the denotational semantic, and I can compute it is equal to 1. So I have proved that my rejection sampling algorithm, which just pick an index randomly, check if the inner is equal to 0, and if yes, it answers this index. If not, it starts again. I have proved that it will end with 1, with probability 1, it will give you an index of a cell that contains 0. And I'm not sure I have much time to do the same thing for Metropolis Hastings, but I can just tell you that I have a way of implementing it in my syntax, and by using exactly the same tool, the operational semantics, the adequacy, the soundness invariance of the interpretation, I can prove that the measure that the interpretation of this program is indeed the Markov chain that is simulating my measure. Okay, so I can conclude with some stuff to take home. First, the semantics formalizes the programming languages in order to reason about programs independently from syntactic choices. Second, semantics of functional probabilistic programming is hard because of higher order programs that are programs that have programs as inputs. But there are several semantics like quasi-Borel spaces or the stable the cones that I've just showed you that allows to ensure that the implementation is correct. And finally, thanks to the operational semantics, to the soundness and adequacy, it's possible to formally prove that correctness. Okay, and I have a few seconds just to say that we have some postdocs available in our project, either in Paris, Bologna, or Marseille. So just follow our, just go to our website and send you an email if you are interested.
Thank you so much for the wonderful talk. We have time for one question that came up from the audience. So you mentioned these with higher order functions at multiple points.
Yeah.
And in the continuous version of the semantics that you proposed, can you give a brief intuition for the trick that helps avoid the issues with the non-measurability of the evaluation map?
So the question is why in the semantics I propose we don't have this problem of the evaluation map, which is not measurable. So the thing we do is just we get rid of measurability and we define a well-behaved model with stable functions. So we have our Cartesian closed category with no measurability. That's the trick. We are not considering all the measurable spaces, but we do have in our model the reals and the measurable spaces that we need to interpret the probabilistic programming. So we are not considering the all, we are considering something smaller and more well-behaved. And then when we have this well-behaved word, we will add measurability as an external tool that is preserved.
Okay, very interesting. Thank you.
And it's something which is quite classical to do, and if it's very similar to what's happened in quasi-Borel spaces and so on.
Okay, thank you very much. We need to move on to the next speaker.
Okay, thank you very much for the invitation.
Thank you.